In 1969, human beings landed on the moon, a fragile machine wrapped in aluminum foil, carrying 3 people, flew 384,000 kilometers through empty space, landed on another world, and came back safely. Then we did it again, and again. In fact, NASA landed humans on the moon 6 different times between 1969 and 1972. Now here's the strange part. After doing something that difficult, we suddenly stopped. Imagine a group of explorers who reach the top of Mount Everest 6 times in a row. They plant flags, collect rocks, take photographs, and then announce, "All right, we're done. Nobody needs to go there again." Wouldn't that feel odd? The common assumption people make is simple. If we could do it once, we can easily do it again. But physics and engineering don't work like that. Going to the moon isn't like building a bridge or manufacturing cars. It's more like balancing a tower of playing cards in a hurricane. You can succeed, but repeating the trick is another matter entirely. So the real question isn't just, why didn't we go back? The deeper question is, how did we manage to do it at all? And once you understand that, the mystery becomes far more interesting. People imagine a spacecraft as a sleek vehicle, like an airplane. But the Apollo rocket, the Saturn V, was something else entirely. It was 110 meters tall, roughly the height of a 3-6-story building, and it weighed about 3 million kilograms when fully fueled. But here's the fascinating part. Almost 90% of that weight was fuel. Think about a car that weighs 1,000 kilograms. Now imagine that 900 kilograms of it is gasoline, and only 100 kilograms is the actual car and passengers. That's what a moon rocket looks like. Why so much fuel? Because leaving Earth is unbelievably difficult. Earth's gravity holds everything tightly. To escape it, the rocket had to reach about 11 kilometers per second. That's over 40,000 kilometers per hour. So the rocket burns fuel to lift fuel, which burns fuel to lift more fuel. It's a strange pyramid of energy. And once the rocket launches, most of the rocket is actually thrown away in pieces along the way, which means every moon mission begins by building something the size of a skyscraper and discarding it. That's not a transportation system. That's a carefully controlled explosion. Now imagine you've left Earth. You're floating in orbit. People think the hard part is over. But actually, the hardest part is just beginning. Reaching the moon is not like driving across a highway. There are no roads, no GPS, no guardrails. Instead, you must launch yourself into a very precise path. If you aim slightly too high, you miss the moon completely. Too low, and you fall back toward Earth. The spacecraft has to enter a narrow corridor through space, like threading a needle from thousands of kilometers away. And then comes another delicate maneuver, orbiting the moon itself. Now remember, the moon's gravity is only 1/6 of Earth's, which means things don't behave quite the way your instincts expect. Landing requires careful control, fuel calculations, and constant adjustments. Even a small mistake could leave astronauts stranded in orbit forever. And yet somehow, they made it work. But that's when the most dangerous part of the entire journey begins. When Neil Armstrong and Buzz Aldrin descended toward the moon, they were heading for something humanity had never tested before: the lunar surface. Scientists weren't entirely sure what it was like. Some worried the moon's surface might be covered in extremely deep dust, fine powder that could swallow a spacecraft like quicksand. Others believed it might be rocky and uneven. So landing was like stepping onto a floor you've never seen, in a room where one mistake means death. And the moon offers no mercy. There is no air, no weather, no rescue team, just silence. The lunar module touched down with only seconds of fuel remaining. Imagine parking a helicopter with the fuel gauge nearly empty, except failure means you're stuck 384,000 kilometers from home. And even after landing safely, the mission was only halfway finished. Because the real challenge was still waiting, getting off the moon again. Here's something people rarely think about. The astronauts didn't just have to land on the moon, they had to launch from it again. Inside the lunar lander was a small rocket designed to blast them back into orbit. Think about that. You're standing on another world, relying on a machine the size of a small car to lift you off the surface and rendezvous with another spacecraft circling above. If that engine failed, there was no backup, no rescue mission. The astronauts would remain on the moon forever. It's like climbing down a cliff using a rope and knowing that rope must later pull you back up. So every bolt, wire, and fuel line had to work perfectly. And astonishingly, it did. Every time. The moon looks calm in photographs. Quiet. Peaceful. But it's actually a hostile place. Without an atmosphere, temperatures swing wildly, from about plus 120 degrees Celsius in sunlight to 170 degrees Celsius in darkness. That's hotter than boiling water and colder than Antarctica. Then there's radiation. On Earth, our atmosphere and magnetic field protect us from high-energy particles from the sun and space. The moon has no such shield. Astronauts had to rely on the thin walls of their spacecraft and suits. Even small dangers become serious when you're so far from help. A torn suit, a damaged valve, a failed oxygen system. Any of these could turn the moon into a trap. People today sometimes assume the Apollo missions were carried out with advanced technology. But here's the astonishing truth. The computers that guided astronauts to the moon had less computing power than a simple pocket calculator. The Apollo guidance computer had about 64 kilobytes of memory. That's smaller than a single photograph in today's world. Engineers had to write programs so efficient that every instruction mattered. They couldn't rely on powerful computers to fix mistakes. Everything had to be calculated carefully beforehand. In many ways, Apollo was not just a triumph of machinery. It was a triumph of human ingenuity. Now let's confront the question directly. If we did it 6 times, why stop? One answer is cost. Each moon mission required hundreds of thousands of workers, massive factories, giant rockets, and enormous amounts of fuel. The Apollo program cost about $25 billion in the 1960s, an enormous sum at the time. To repeat those missions again and again would require continuing that massive effort. It wasn't just building rockets. It was maintaining an entire industrial machine dedicated to reaching the moon. And once the goal had been proven, the urgency faded. Another piece of the puzzle is historical. The moon missions happened during a fierce technological competition between nations. Landing on the moon was not just exploration. It was a demonstration of scientific and engineering capability. Once that race had been won, the motivation shifted. The question changed from, can we reach the moon? To something more subtle. What should we explore next? Sometimes exploration slows not because something is impossible, but because the original reason for doing it disappears. So, the mystery of why we stopped going to the moon isn't really a mystery at all. The Apollo missions were not routine travel. They were a rare moment when science, engineering, politics, and curiosity all aligned. A fragile window of history, when thousands of brilliant minds focused on one astonishing goal, and together they reached another world. The real lesson isn't that returning to the moon is impossible. It's that the universe doesn't hand us discoveries easily. Sometimes reaching the next step requires not just technology, but the collective determination of an entire civilization. And when that determination appears, human beings can accomplish things that once seemed completely impossible.